Welcome to Business Analytics. This video is an example of using linear programming for logistics or transportation or supply chain management. Okay, so the goal is to find the minimum cost solution to transport goods from multiple sources to multiple destinations. But we have some constraints, and the constraints are we have a supply constraint at the sources and we have a demand constraint at the destinations. And this is just a very simple case where we know what the routes are, and the issue is how much to send down each route. Okay, it's not the more complex case where we have to find a route for minimum cost for just one shot. And to do the second case, you need integer programming, which is a lot more complex than what we're looking at. So, very simple example. I love simple examples. This is, we have three different sources. Busan in South Korea, Shanghai in China, and Singapore in Singapore, and they're sending containers to four places in United States: Albuquerque, Chicago, Denver, and El Paso. And so we have a supply constraint where we have 50 containers in Busan, 30 in Shanghai, 20 in Singapore. And then we have demand. We need to get 5 containers to Albuquerque, 55 to Chicago, 30 to Denver, and 10 to El Paso. Okay, of course, we have the cost here. These costs are kind of based on the distances and with a little bit of fudging around. And so just to go from Busan to Albuquerque is 3,067. Which is the smallest. So you might think, oh, everything from all of Albuquerque's demand will come from South Korea. And then what's maximum here is Singapore. Okay. So the problem is pretty simple. We're going to put the containers on container ships, send them either across the Pacific Ocean or the Atlantic Ocean, and then they'll arrive in Long Beach, California. Okay. And then once they come to Long Beach, they will be unloaded, put onto trucks, and headed off to their final destinations. All right. So this is a worksheet for the total cost, and this is in matrix format. Okay. So because my cost is in a matrice, right? You can also put your decision variables in a matrix and then go ahead and fill it all out. And so the total cost is just the sum product of my decision variables, which are down here in the blue, the number of containers I send from each source to each destination. Those are my decision variables. It's the sum product of that times the cost up here. So, it just takes B2 times B9 plus C2 times C9 plus, and so on, and you come up with the total cost. Next, we have how much do we ship from S2? S2 is Shanghai, and it's just a sum. Okay, no sum product, no dollar signs around sales or anything like that. Just the sum, and I just copy and paste that for the ship. And then for destination to Chicago, how much goes into Chicago? It's just the sum down the column for Chicago, just for the decision variable. Okay, and so I have my supply here: 50 containers in Busan, 30 in Shanghai, and 20 in Singapore. And then down here I have demand. Albuquerque needs 5, Chicago needs 55, 30 for Denver, and 10 for El Paso. Okay, and so I have a less than or equal to constraint because I don't want to ship more than I have, and I have less than or equal to constraint here because I don't want to receive more than what I need. All right, so what happens? We set the objective function up here, cell D7. The changing cells, I just highlight the entire range, B9 through E11, right? So if you just highlight that, you get that. And then I have the supply constraints and then also the demand constraints. Here, they're in 2 different locations, so I had to put them in twice. Make unconstrained variables non-negative. Sure, why not? Simplex LP, hit solve, and boom, there's our solution. Is that a good one? Well, our total cost is 0. That's good. We don't want to have a cost. And we get a 0 cost by shipping 0 containers. So you just found something out, right? You can go to your boss and say, hey, boss, guess what? We don't have any costs if we don't ship anything. And your boss will say, that's great. You're fired. Okay. You don't ship anything, you don't make any money either. So that's a bad thing. So what happened? Well, when we're doing cost minimization, we have to have some bigger than or equal to constraints, right? We have to have something in there to make sure things ship. Otherwise, just like we saw, it just says, hey, don't ship anything. That's how you minimize your cost. So this is a covering problem where we want to find a minimum cost solution, but we need to achieve some objectives, right? We have objectives here. The objectives here are satisfying the demand at the different destinations. So we need some bigger than or equal to constraints. Now, some fine detail, if your total supply is equal to your total demand, which we have in our case, right? So if we go back, our supply is 50 plus 30 plus 20 is 100, and demand is 60 plus 30 plus 10, which is 100. And so 100 is the same as 100. Supply is demand. And so what I need to do is just change these constraints to bigger than or equal to. You run into a little bit more complication if total supply is bigger than total demand, in which case you're going to have the bigger than or equal to constraint on the demand. And if total supply is less than total demand, you use bigger than or equal to on the supply constraint. Okay. Now, yeah, is that a big deal? Well, if you don't get it right and you run it, and solver's going to blow up and give you a strange answer or say we cannot find a solution, in which case you got to go back and rethink it. Okay. So, just have to be aware that, sometimes you run solver and you think you're looking good, but it doesn't work out so well. All right. So here we go. We changed the constraints to bigger than or equal to. We have the same objective function, same changing cell, just change. What I did is I hit change, I highlight one, hit change the constraint, highlight the other one, hit change. Simplex LP, click solve, and there's the solution. So the minimum cost solution is $417,000. And what's the shipping? Well, out of South Korea, we send 5 to Albuquerque, 25 to Chicago, 10 to Denver, and 10 to El Paso, and that's a total of 50, right? So when you have this bigger than or equal to, you're not going to ship more than you need to, right? Because if you ship more than what you need to, you're incurring a cost for no apparent benefit. So that's fine. For Shanghai, we ship 30 to Chicago, and for Singapore, we ship all 20 to Denver. And then you can see here how much arrives at the destination. We're making 5 at Albuquerque, 55 at Chicago, 30 at Denver, and 10 at El Paso. And again, you're not going to ship more than you need, because if you do, right, if I send 35 to Denver, well, it just increases my cost. And since I'm doing cost minimization, solver won't let you do that, won't go there. Okay, so I'm not a big fan of the matrix formulation, right? This is the matrix formulation. I've seen a lot of people's spreadsheets over the year, and they're not consistent with what they do with the matrix formalization. They put the constraints every old which way, and when you look at their spreadsheet, it's really hard to analyze what's going on, right? So if you give your spreadsheet to someone, they might have trouble figuring out what in the heck your model is. But here's how you would vectorize it to get it into what I consider a normal form, where you have your objective function up here at the top and just strung out in a long row instead of a vector. You have your cost strung out in a long row. And then we would be using a sum product where we put dollar signs around the blue cells, $B, $2 to $M, $2. So we're always doing absolute addressing to my decision variables. And then I have the cost coefficients here, just strung out, right? I just took each row of the cost matrix and put it out there, okay? And so if I go back, you can just see that, right? Here's the first row. It's going from South Korea to the destinations, United States, and that's what I have here. And then the second row is from Shanghai to United States, is the second piece here. And the third piece is from Singapore to United States. Okay, and so the sum product will give you the total cost. And then once I have that sum product, I just copy and paste it down here. What are these things? Well, this shows you what the equation is. First of all, if it's a blank, Excel treats blanks as zeros, right? So I can just leave blanks in here instead of putting down zeros. But this is just going to say, hey, I take one. Let me see, I have it on the next one. Nope, I have solver. I take 1 times 1 plus 2 times 1 plus 3 times 1, and then the rest are 0, and that gives me the 6, right? So it's basically just 1 plus 2 plus 3 to give you the 6. And so this is my supply for coming out of Busan. This is my supply coming out of Singapore, and this is my supply coming out of, I'm sorry, this is Shanghai and then Singapore, okay? And now the destination looks a little bit different. Okay, so up here it's S1D1 is how much I shipped from Busan to Albuquerque. S2D2 is how much I shipped from Shanghai to Chicago. S3D3 is how much I shipped from Singapore to Denver. Okay, and so if I'm saying how much is going into Denver, I just look for everything with the D1 that has a D1, right? And so it's this guy, put a 1 there. So 1 times 1 plus 1 times 0 plus 1 times 0 gives me the 1. This is everything going into Chicago. I have 2 going into Chicago there, 0 there, 0 there. So that's where the 2 is, and so on. So that gives me my supply, and then also my demand. It's always bigger than or equal to. So this is just like the other examples on Solver where it's strung out like this. I like to think of it as a normal form. Anybody can come in here and find out where the objective function is and what the constraints are and the equation for the constraints. Okay, so I'll just set up as we always did. You just hit N3 is what I like to minimize by changing B2 through M2, just that row. And then the constraints are all just one constraint bigger than or equal to. These guys are bigger than or equal to those guys. I hit solve and I get the same solution as I had before, right? So all the constraints are satisfied, same cost, and same decision variables. Okay, good fun. Here's a transshipment problem. In the previous case, everything went through Long Beach, California. Okay, and then they were put on trucks and went to their final destination. What we're going to do is expand that, saying we can ship to Long Beach on container ships, or we can ship to Houston, Texas, right? And so if you go to Texas from either South Korea or Shanghai, you'd probably go through the through the Panama Canal. But if you went through from Singapore, you go through the Suez Canal. Okay, and so it's longer, it's more expensive because you have to go through a canal. But once they get there, once all the containers get at Long Beach or Houston, then they're put on trucks and shipped to their destinations. So there's really 2 sets of decision variables. Do you want to ship to Long Beach or do you want to ship to Houston? And then once your containers end up at Long Beach and Houston, they get off the container ship onto semi-trucks, and then from there, they're allocated to the different cities in the United States. All right, so here we have new cost functions because we have a Long Beach and a Houston, and this is just the cost from shipping from the different suppliers in Asia to the ports in the United States. I call them T1 and T2 for transshipment point at Long Beach, transshipment point 2 for Houston. And then once they get into Long Beach or Houston, then they're shipped out to the cities in the United States by truck. So those are the costs broken down. Okay. And then here's a naive workbook, which maybe is a clue that something's coming up. But here's my cost. I just made a matrix out of it, right? So this is shipping from Busan to Long Beach and then Busan to Houston. And then down here, this is the cost from shipping from Long Beach to Albuquerque. I assume shipping costs are symmetrical, so it'd be the same as going from Albuquerque to Long Beach if you were sending it back. Okay, so we have the cost broken down like that. Now the decision variables are just the amounts. So this one is the amount I shipped from Busan to Long Beach. The two is the amount I shipped from Shanghai to Houston. Okay, these down here kind of got to think about going the other direction, right? So this is the amount I go from, the two here is the amount I go from Long Beach to Chicago, and then Long Beach to Denver is the other two, and then from Houston to Albuquerque, and then Houston to El Paso. Okay, so the direction, these guys go this way in shipping, and these guys go that way, right? You're going back to the city. So anyway, it doesn't really change much. It's just a sum product for total cost. Just take this whole matrix, actually two matrices, and hit this with sum product with this matrix. Okay. Now, what I have here is, well, how much is being shipped out of? Let me see. Do I have that one? Okay. How much is being shipped out of Shanghai? Well, all you do is the sum. So you just add 0 plus 2, the sum, and that will be how much you ship out of Shanghai. So all of these shipped is just the sum of these guys, right? How much is, this is this amount being shipped from Busan, this is Shanghai, this is Singapore, so that's my supply. Demand is, well, how much does Albuquerque get? Well, Albuquerque gets 0 plus 1 or 1, Chicago gets 2 plus 0 and 2, and so on. So this is how much is arriving in the different US cities. And again, this is all bigger than or equal to signs. And, here's the solver dialog box. The total cost is there by minimizing the blue, right? The amounts in blue, and subject to the constraint, the amount that we're either shipping from the locations or receiving at the destinations are bigger than or equal to the supply or the demand. Okay. And again, simplex, you hit solve and come up with a solution. The solution is bad. Why? Why is it bad? Well, my cost isn't 0. Things are being shipped, but there's a little bit of magic here. Okay, I'm shipping everything from South Korea to Long Beach, everything from Shanghai to Long Beach, everything from Singapore to Long Beach. So I have 100 containers sitting at Long Beach, but I'm not shipping anything out of Long Beach. So the harbor master of Long Beach is going to get really peeved at me for having all my containers stacking up in Long Beach, taking up the space that he or she needs, right, to operate their terminal there. Well, that's pretty bad, but even more magical is that nothing's going into Houston. Bunch of goose eggs. But look at that. We're shipping stuff out of Houston. Okay, so we're shipping 5 containers from Houston to Albuquerque, which is its demand, 55 to Chicago, which is demand, 30 to Denver, and 10 to El Paso. So I don't know. Maybe there's some way that they do some sort of black hole or something that these guys fall into in Long Beach and then magically appear in Houston. But obviously, some sort of magic going on. Obviously, you can't do that, right? So what's the issue with it? Well, we have these transshipment nodes. These ports are transshipment nodes, right? They're not the final destination. We have containers going in. We need containers going out. And we have to make sure that what goes into T1 comes out and what goes into T2 also comes out, right? So we're shipping from the sources to the transshipment nodes to the final destination. Okay, so this is a network model. Okay, And so to do that, we need balance equations, right? So what comes in, the in arrows are equal to the out arrows. The amount coming in has to be equal to the amount going out. And so for Long Beach, what comes into Long Beach, right? It comes in from Busan, from Shanghai, and Singapore, and then it goes out. So this is coming in, and this is what's going out from Long Beach to Albuquerque, Chicago, Denver, and El Paso. Same thing for Houston. This is what's going into Houston from our Asian ports, and this is what ships out of Houston to our U.S. cities. Okay, so in Solver, though, you don't want variables on the left side and variables on the right side. You want to move all your variables to the left-hand side. And so that's all we did down here, right? So we have what comes in minus what goes out is equal to 0. So now we have to go back and modify our Excel, our solver model, and I just put them down here. Okay, so this is the balance equation for Long Beach, right? And so what I did is just sum up these guys, right? 50 plus 30 plus 20, summed up those guys, minus the sum of what arrives in the different cities from Long Beach, okay? And the same thing, I did the same thing for Houston. I summed up what goes into Houston, 0, 0, 0, minus what goes out of Houston, which is, some of these guys. So zeros minus some of these guys is minus 100. Okay. Now, when I put that into Solver, I could just I have to use the equality constraint. Okay. I'm not an operations researcher, but from reading their textbooks, it seems like they do not like to use equality constraints. They prefer to use bigger than or equal to or less than or equal to, like we did with supply and demand. Like we could have put equality constraints in. But this is a situation where even operations researchers would have to put in equality constraints, put a equality constraint in. And in Solver, instead of having a separate cell, I just put a 0 in, right? I just typed in 0. And so there it is. And then when you run it, again, minimization, all that, same as before, you run it and you get a solution. Your total cost is $414,198. Our balance equate, we balance right. We have 80 going into Long Beach, and we have 80 coming out of Long Beach. We have 20 going into Houston, and we have 20 coming out of Houston. We're using up all of our supply. We ship everything that's sitting at our source locations, and we're meeting demand at all of our destination locations. So that's a good thing. And so from out of South Korea, we ship 50. All 50 go to Long Beach. All 30 from Shanghai goes to Long Beach, and all 20 from Singapore goes to Houston. So those are going through the Suez Canal and across the Atlantic Ocean, those 20 containers. And then what happens? Well, the 80 in Long Beach get broken up into 40 to Chicago, 30 to Denver, 10 to El Paso, and the 20 from Houston gets broken up into 5 to Albuquerque, and then 15 to Chicago. It's kind of interesting that even though El Paso's in Texas and Houston's in Texas, it's less expensive to ship to Long Beach and then haul it across the Rocky Mountains than it is to ship it to Houston and then drive across Texas. All right. So that's the solution. This is how you'd represent it. So again, on this picture, we have 50 at Busan, 30 at Shanghai, 20 at Singapore. And all 50 go to Long Beach, all 30 goes to Long Beach. And then Shanghai, all 20 goes to Houston. And then from there, Long Beach is 40, then 30, then 10. And to D2, D3, and D4 are Chicago, Denver, and El Paso. And then out of Houston, we send 5 to Albuquerque and 15 to Chicago. Okay, and so that's a graphical representation of the model, and it's $414,000. Great. All right, we could also put a port capacity in. So I hope this doesn't happen, but let's suppose a ship carrying ammonium nitrate explodes in Long Beach. And now Long Beach has a constraint. We can't ship as much as we want to Long Beach, but we can only ship 70 containers, right? And so if we go back and look, we're currently shipping 80 containers, but now we can only ship 70. And so we didn't want to know how the solution changes. So I put that constraint in, and again, with this matrix things, you just kind of like put it in wherever you can find room. But I just took the sum. Okay, how much is going into Long Beach? What's the capacity? It's these three cell B11, B12, and B13. Okay, that's the sum, and that has to be less than or equal to 70. I just go ahead and add that constraint to my model. So D18 is less than or equal to F18, and everything else is the same. And then I just go ahead solve, and what do we get? Well, now all 50 of South Korea still goes to Long Beach, but Shanghai gets split up, right? Only 20 goes to Long Beach and 10 goes to Houston. Okay, that's 30. And so these 10 had to go across the Pacific and the Panama Canal up to Houston, where Singapore is still shipping 20 through the Indian Ocean up to the Suez Canal, out the Mediterranean, across the Atlantic to get to Houston. Okay. So these 70 from Long Beach, 30 go to Chicago, 30 goes to Denver, 10 goes to El Paso. So that satisfies our balance equation, right? 70 plus 7 minus 70 is equal to 0. In Houston, we're sending 5 to Albuquerque, 25 to Chicago, and that satisfies our balance equation. We have 30 in Houston, and we ship out 30. So the balance equation is 0. And then you can see we are shipping everything from our source location, and then we're meeting our demand at our destination. And we have the capacity constraint at Long Beach is 70, and of course we're using up that capacity. All right. And this is just a modification, so now we can see that the big change here in shipping from the sources to the transshipment point is that Shanghai splits the load 20 to Long Beach and 10 to Houston, and then the loads are shipped out from there, and some modification 30 and 30 and 10, and then 5 and 25. Okay, so our cost went up, right? If you added an additional constraint, your cost can't go down, it has to go up again, and it went up by a small amount. All right, and here's the vectorized version, or I like to call it the normalized form. And so we have we have the supply constraints. Okay, just stretched out once again. This is Busan to Long Beach, Busan to Houston. This one is Shanghai to Long Beach, Shanghai to Houston. How much goes there? The third one is Singapore to Long Beach, Singapore to Houston. And then the containers coming out of the ports, right? So this is Long Beach to Albuquerque, Long Beach to Chicago, Long Beach to Denver, and Long Beach to El Paso. And then we look at Houston to Albuquerque, Houston to Chicago, Houston to Chicago, Denver, and then El Paso. Okay. And so how about the supply? Well, this is the stuff coming out of S1. It's just the sum of those two. This is coming out of S2, out of Shanghai, right? So you go 50 times that plus 0 times that. Here's 20 times that plus 10 times that to give you the 30. And here it's 0 times that and 20 times that to get you the 20. And then demand, you just look for everything that, for demand for D1, which is Albuquerque, you just look for everything ending in D1s. So we're picking up this cell, and we're picking up this cell. So it's either from Long Beach or it's from Houston. So it's 0 times 1 plus 5 times 1 gives you the 1. And then come on down to D2, Chicago. There's 30 at Long Beach, and then there's 25 at Houston to give the 55. And the same thing for Denver and El Paso. The balance equations, look for everything going into Long Beach, which is the T1. And that's what we're picking up with the plus ones. Look for everything going out of Long Beach, which are the T1 to the destination. So I put a -1 there, right? So basically I'm taking the sum of 50 plus 20 plus 0 is 70. And then what comes out is these guys, 30 plus 0 plus 30 plus 30 plus 10, 60, 70. And so we have minus ones. Same thing for the balance equation for Houston, same kind of thing. And then we have a capacity constraint. How much can we ship to Long Beach? Well, it's just everything with the T1 here, right, on the supply side, okay? And so we have less or equal to 70 here. So I just have, again, a sum product that I copy and paste down. The sum product has, these cells with dollar signs around, the decision cells with dollar signs. When I paste it down, I get that. And this is the solution, same solution as we had before. Okay, great. Okay, logistics is great fun. It's a really big deal. In the example we're looking at, I just read in The Economist, I think a couple of weeks ago, that there's something like 1.2 million people on container ships around the world, right? So it's a huge trade on container ships. It's really the backbone of the global economy. If you roll back time, like, I don't know, 20 or 30 years ago, container ships were not that effective, not that many of them, but it's really revolutionized the business. Logistics, of course, you have not only container ships, but you have trucks, you have trains, you have planes. So the linear programming has had a huge impact. Everybody is trying to run as efficiently as possible. You end up with models with thousands of variables in it, right? So I just picked 4 towns, one large one, Chicago, one smaller, well, not middle-sized, Denver, then 2 smaller ones. Okay. But you have hundreds of locations you're shipping out of and hundreds of destinations. All right. You have all kinds of constraints. Don't use Solver if you do this for real. You have to use a more commercial package. Plus, you frequently update these things, like probably daily, right? As things leave port and come in port, or planes take off and land. Every day you have new packages that need to be shipped. So you might have to update these models frequently. And you have huge data flows, right? So all these ships and planes and trucks and trains are all being tracked. Lots of times packages themselves are being packed, or containers themselves are being tracked. You got to keep tabs on all that stuff. And so it's really a case of business analytics where data science, right? All this data flowing in, that's all has to do with data science to find out what the efficient solutions are. And, the environment changes all the time, right? So if you have a change in petroleum prices, or whatever that sludgy oil they use in container ships, right? Boy, that stuff is polluting. If you have a change in that price, you might change your solution, right? So you might want to update it. COVID caused a really, really big issue because obviously with COVID, some ports are closed. Some ships are stuck at sea. Some sailors have been, they typically have something like a 3-month contract. And they're working hard, right? Because they're probably doing like 12-hour shifts, 7 days a week. And some sailors have been on their ships for over 6 months now, and they can't land. Countries will not let them disembark in their countries. And even if they did disembark the ship, they can't fly home. They can't get home. So it's been really tough on those sailors. Okay. Much easier just being a professor and doing YouTube videos. Okay. Network models. This is a special case of a network model. And it's used in a lot of other settings like communications, production, inventory management. I like the one on cash flow. So it can be used in finance, right, for cash flow management. Here's just a fun picture of the internet by Kaspersky Daily. And they're a security firm, IT security firm, and they plotted out the internet, which websites are connected to other websites. I don't know what you do with this, but boy, it's just fun to look at. Here's a car manufacturing process in an assembly plant. So The assembly plant has three big operations: the body shop, which brings in rolled stills and have these huge multi-million-dollar punches to take the rolled still and make them into fenders and hoods and all those kind of things, doors. And then the body shop welds those together with robots. You go into one of these body shops, you hardly see a person around, except for a couple, maybe engineers and repair people. And then after the car's put together, it looks like a big old tin can with holes in it. Then it goes into the paint shop where they first dip it in. Well, first they clean it, then they dip it in a primer and they dry it, and then they do a color coat on it. And you have robots painting it, right? You don't see people there with spray guns. You see robots doing it. And they dry it again. They put a clear coat on it, and they dry it again. And then it goes in the assembly plant where the body shell gets married to two subframes. The front subframe, if it's a front drive car, front wheel drive, it has the engine, the transmission, and the wheels and suspension all held in a subframe that gets bolted onto the body. And then you have a rear subframe, which holds the rear suspension and rear wheels that gets bolted onto the subframe. Then after it leaves the plant, it goes to dealers. Unless you're Tesla, they don't have dealers. Good for Tesla. Goes to dealers, and there's marketing and financing going on at the dealers from the auto company, and then it goes to customers. So you can represent that as a network of different operations where you have cars going through here. You have information flows. You have things like scraps, pollution, defects coming out, so you can write that down as a network. Here's inventory management, right? So this is over time. These kind of models are great for managing things over time. So you like to coordinate your production over time to meet your demand. And so you're delivering goods, but you're producing goods. And so you use your inventory as a buffer to smooth out your production. For example, your demand may be non-constant, kind of spiky, depending on time of year and other factors. But typically your production facilities are kind of like running more or less constantly. You can put on more shifts or more hours, but you don't want to introduce a new factory, right? That's could be very expensive. And so you're putting some of your production into inventory. And so the big question is, how do I set my production schedule to meet my delivery to minimize production and inventory costs, right? And so the whole key here is just like the transshipment problem. You have a balance equation at each time period. Okay, so you have like the balance equation here is you have inventory coming in, you have production coming in, and what do you have coming out? Well, you're having inventory go out in the inventory at time one and the delivery at time one. So this guy plus this guy is equal to the inventory at time one and how much you deliver at time one. Okay, so you have one of these balance equations at each one of the nodes. Okay, that's how you can do inventory management. Here's a really great example of if you're going into finance, which finance kind of pays more than operations, so maybe it's not a bad idea. It's managing cash flows is something you do in finance, right? You figure out how you're going to raise money to achieve your goals, and then also how you manage your cash flows. And so the basic idea is that each time period, well, actually you start with the initial investment. Okay, you set up your whatever business model you have, right? You hope you have a cash-making machine, a money-making machine, but you have money coming in from, let's say, your sales. The business might be holding bonds or some other things, securities, so they have money coming in. And then you have money going out, which pays for things like your labor, your financing expenses, your capital equipment, your taxes, all these things. So you have money coming in and money going out. If you're a capitalist, which I assume you are if you're watching these videos, capitalist or residual claimants, the capitalist or the owners get the difference between the money in and the money out, right? But you have some working capital, and that working capital at time one is this kind of like your inventory, kind of like your inventory of money gets it goes into time two. So again, at every single one of these time points, you have the balance equation, right? So what was your working capital from the previous month, how much money came into your business, how much money came out. That gives you your working capital at that time too. So if you take the money in plus the money from the previous time, that's going to be equal to your money out and your money that you have at time two. So you have these balance equations at each time point. Okay. So what we want to do is find out, well, how do you maximize net present value subject to funding constraints? Okay. And we have these balance equations. All right. So the next slide's kind of goofy. I saw this on a BBC website and I thought, whoa, this is cash flows. This is our cash flow, but they represent as a leaky toilet. So we have revenue coming in through this pipe, capital coming through this pipe. I've never seen a toilet that maybe has hot water and cold water. Where did the profits come from? I hate to say the profit comes from the bowl of the toilet. And it's a leaky toilet, so we have what wages come out here, and we have expenses are leaking out, bills are leaking out, and then our net cash flows here. All right. So, well, maybe with Brexit now, England's becoming irrelevant and they have to do funny cartoons instead of actually running businesses. Okay, great. Well, hey, thanks so much for viewing the video. I hope you enjoyed it. I hope you learned something from it. Please, if you did enjoy it, if you did learn something, please give me a thumbs up and hit that like button. And I hope to see you in future videos. So long now.